Alrighty, good afternoon, lads and ladies. Today is more or less your day. We can talk about whatever you guys would like. I do want to make sure we spend a little bit more time working on rational inequalities, since we haven't had a lot of time to talk about them yet. But feel free to pop up the quiz/review in WebAssign and take a look through there for anything that you would especially like to see solved or discuss. As today is our exam 2 review. Remember, your exam 2 is next Monday during class time. While you're perusing, I am going to list the topics and sections on the test. This is one of our kind of shorter tests, or a test that covers not a lot of sections, but the material therein is fairly technical, right? We've had all those theorems on polynomials, all these factoring tricks and synthetic division, and all the graphing stuff with multiplicities, rational functions, asymptotes. So of course, it is worthwhile to recap exactly what it is that's going to be on here. So that is not you, this is you. There we go. All right. Last time, remember that we were very gentle on inverse functions because we covered inverse functions just before exam 1. So section 2.8 will be making a comeback here. I warned you that that was the case. So we'll say sections 2.8 on inverse functions, and then 3.1, which is on quadratics. Section 3.2, which is on polynomials, specifically polynomial graphs. Section 3.3, which is on dividing polynomials. And it was here that we talked about like the rational roots theorem, roots theorem, the factor theorem, synthetic division, what else was there? The remainder theorem. So all of those topics fall into dividing polynomials. 3.4 and 3.5, if I remember right. Yeah, 3.4, 3.5, that stuff. So then we had complex roots. .5 and 3.6, these are on like complex and real roots of polynomials. So this was where you had to do things like tell me a polynomial with integer coefficients that has roots 1, -5, and 1 plus I. Here you want to remember things like if a plus ib is a root, then so is a minus ib. This is for polynomials with real coefficients. Roots always come in complex conjugate pairs. That's something that folk often forget. You might want to add a little note to remind yourself. Nothing else especially heinous in those two sections. And then we had 3.6 and 3.7. Oh, I'm sorry, this is 3.5, isn't it? 3.6 and 3.7 and 3.7, 3.8. Yeah, sorry, just 3.5 here. And then 3.6 was on rational functions.
Hey, sorry, can you show your writing?
Yeah, is it not? Oh, shit. I didn't realize it wasn't displaying. Thank you. Thank you, yes. Sorry, usually I get little notifications when something is in the chat that I haven't seen, but it wasn't blinking there. So yeah, thank you for speaking up. So sections are 2.8, 3.1, 3.2, 3.3, 3.4 and 3.5. That's these. I wrote 3.5 and 3.6 originally, should be 3.4 and 3.5. And then 3.6 is on rational functions, graphing rational functions mostly, finding domains, vertical asymptotes, horizontal asymptotes, all that good stuff. And then 3.7 is the one that we learned last time. This is on nonlinear inequalities, specifically rational and polynomial. Okay, so these are the sections on the test. It's really not a whole lot, it's 2 chapters. But the chapters are fairly dense, a lot of like theorems and a lot of kind of technical stuff in here. So you'll certainly want to make sure you remember all of the theorems and make sure you're comfortable with all the procedures. Inverse functions, the only thing from chapter 2 that's showing up here again, and this is only on this test because we barely touched it on exam 1. So make sure you remember what it means for a function to be 1-to-1. Make sure you remember the definition of an inverse function. Make sure you know how to graph the inverse of a function just from the graph of the original function. Make sure you can solve for the inverse of a function. Remember the relationships between domain and range of the original function and the inverse, all that stuff. Quadratic functions, make sure you remember how to complete the square. That's something that folks tend to forget. So here under inverse functions, I'll say graphs of f and f inverse, domain and range. Remember, the domain of f is the range of f inverse, and the range of f is the domain of f inverse. Those sort of things. Under quadratic, stuff people forget is like mostly just completing the square. Everything else in that section should have been reviewed. Polynomials and polynomial graphs. This is all stuff we've been talking about recently, so hopefully it's still fresh in your head. Polynomial graphs, make sure you remember the multiplicity thing, like bouncing versus crossing. Dividing polynomials, make sure you remember the theorems I've listed there. Complex and real roots. You know, the only thing that people tend to forget there is that if you have a polynomial with real coefficients, then any complex root will always show up as a part of a conjugate pair. And then the 2 sections that we learned in the last week or so. Rational functions and nonlinear inequalities. The test will be about the same length as exam 1. I haven't written it yet, but somewhere between 10 and 20 questions, a few true false, a few multiple choice, and a few free response. And the question weight will be about the same as, well, will be the exact same as it was on exam 1. So the true false worth some amount, the multiple choice worth a little bit more, and then the free response worth a little bit more. The ratios are 2, 3, 5. Yeah, I heard that there have been problems with the videos I posted for the last 2 lectures. So this morning I went into my YouTube account, deleted both of those, and re-uploaded them. One of them was actually already deleted. I'm not sure why. YouTube might have, maybe there was a song playing in the background somewhere in my apartment I couldn't notice, or Maybe I swore in a way that they weren't happy with. I don't know why. But in either case, there are fresh links to freshly uploaded versions of both of the last 2 lectures available now. So I fixed all of that if you're having trouble watching those videos. All right, so these are our topics. What would you guys like to do? We got about 60 minutes left today where we can solve whatever you guys would like to solve. So are we talking about from the quiz or from the study quiz or the homework? Okay. And Lily, are you talking about problems from the quiz? From homework? Okay, homework 6, number 9. Or maybe homework 7. The newest one. All right. So yeah, I think Lily put in the first request there. So let's take a look at this. This is good. We'll solve this inequality. I'm going to write it down. So this is homework 7, number 9. Solve x minus 6 over 2x plus 3 is greater than or equal to 1. That's correct, Leonie. You have until Monday to work the quiz. So you should work the quiz as soon as possible. And that way you can come to office hours, email me questions, all of that stuff. And then the test itself is on Monday. So you can think of the quiz as like your study guide or your review, right? You can work those problems up until the day of the test. And then the test is Monday during class time. I do not recommend waiting until Monday to do the quiz. I strongly recommend doing the quiz like today, tomorrow. And that way we can talk about anything that you get in trouble with in office hours or through emails or Canvas messages or whatever over the weekend. But then yes, the test is Monday. All right. Who can help me with this inequality? You remember the procedure for solving these? Yeah, we got to start by pulling everything over to one side. So my first step is to rewrite this as x minus 6 over 2x plus 3 minus 1 is greater than or equal to 0. So we pull everything to one side, so it's 0 on the other side. And then what's our next step look like? Or what should we do for our next step? Good, common denominator. We got to write everything as one big lump and then factor top and bottom. This is true for all nonlinear inequalities. Pull everything to one side, write as a single chunk, then factor everything. So this is going to be x minus 6 over 2x plus 3 minus 2x plus 3 over 2x plus 3 is greater than or equal to 0. And then I put those together into one fraction. That's the point of having a common denominator. When I do that, I need to make sure I distribute this negative to both the 2x and the 3. So I'll have x minus 6 minus 2x minus 3 all over 2x plus 3 is greater than or equal to 0. I'm going to continue over here. I'll combine the like terms in the numerator. So I have x minus 2x, that's negative x. And then I've got minus 6 minus 3, that's minus 9, all over 2x plus 3 is greater than or equal to 0. And there's not much in the way of factoring to do. I can factor a negative 1 from the top. And that gives me this. So, all right, we've done all the kind of nasty algebra stuff we need to do here, pulling everything to one side, common denominator, like terms, factoring. What do I do once I get to this place? We had a special name for the things we need to find now. Yeah, we're gonna need a number line, and on that number line, we're gonna plot our special numbers. So what are the special numbers here? Those are numbers where this object is capable of going from positive to negative, which would be anywhere the top or bottom is equal to 0. Yeah, there's two of them here. They are -9 and -3/2. We always find these by setting the top and bottom both equal to 0. Perfect. So remember, -3/2, that's -1.5. So when I put these on my number line, I need to make sure the 9 is to the left of the -3/2. So over here, we'll call this -9. Here, I'll call this -3/2. And then there's more than one way to proceed from here. The fastest way to proceed from here is to think about end behavior and multiplicities. The slow way to proceed from here is to test a point from each region. So from the region on the far left, I could test -10. What that means is I would take -10 and plug it in for x in this and write down the sign I get. So if I plug -10 in upstairs here, I'd have -10 plus 9, which is -1. The negative of -1 is +1, so the numerator would be +1. And then downstairs, I would have -10 times 2 plus 3, which is -17. So I'd have +1 over -17 would be negative. Or if I'm feeling sneaky, I can use the end behavior. So the horizontal asymptote for this function is -1/2, which means as I wander really, really, really far off to the left, this function gets closer and closer and closer to -1/2. In particular, it's negative. Either way, I learned that to the left of -9, this function right here is negative. Everybody follow that? Two ways of figuring out the sign here. We could test x equals -10. Or anything to the left of -9. You could test x equals -20 or -9.5. When I do that, I get -1 over -17, which is +1 upstairs over -17 downstairs, which is negative. So I write negative here. Between -9 and -3/2, I could also test something like -2, or I can use the multiplicity trick. As I jump over -9, is this going to stay negative or is it going to become positive? Good, we're going to change sign. Why? Yeah, because the -9 came from this factor, which is a multiplicity 1 factor. Since the multiplicity is odd, I know I will change sign as I jump over this. So we're going to go from negative to positive here. Or again, if you test something like -2, upstairs I would have -7. Downstairs I would have -4 plus 3 is -1, so negative over negative is positive. Then as I jump over the -3/2, will I change sign or will I stay the same? So I'm positive in this region, we've just discovered that. And the question is, as I hop over this, will I stay positive or will I change to negative? Yeah, Lily's got it. The answer there is we'll change again to negative because the negative 3/2 is coming from this factor downstairs, which is also multiplicity 1. Since 1 is an odd number, the multiplicity is odd. That means we will change sign. So we will go from positive back to negative. If you wanted to test something from this region, 0 would be a good thing to try because 0 is definitely to the right of negative 3/2 on a number line. And plugging in 0 is easy. So the top would be -9, the bottom would be +3. That's -3, that's negative. But really you only ever need to test one region. Sometimes you don't even need to do that if you use the information from the horizontal asymptote. But at most, you should only ever need to test one region. That makes these problems go quick once you get to this step. All right, we got our number lines. So now we just need to write down the answer. Which of these regions is included in my solution set? Is it the plus stuff or the minus stuff? Yeah, the plus stuff, because I'm asking, where is this stuff greater than or equal to 0? That means I'm asking, where is this stuff positive or equal to 0? So it's the middle region that will be giving me my solution. So the solution set, this is an inequality, it's not just one number, it's a set of numbers, is the interval -9 to -3/2. And the last thing I need to do is ask whether I should use parentheses or brackets. Because this is a greater than or equal to, it is possible that we'll need some brackets. But it will not be brackets on both sides. If you plug -9 into this expression, you get a true statement. You get -0 over -18 plus 3 is -15. So 0 over 15, that's 0. And 0 is greater than or equal to 0. So this is good. But if you go plugging -3/2 into this expression, you make the denominator 0, which makes the whole thing undefined. And being undefined means I cannot include this value in my solution set. So I have to use a parentheses over here. Yep, you can plug in, or the kind of easy, I wouldn't say easy way, but if you want to remember a rule, you only ever have to ask this question if you're looking at an or equal to type inequality, greater than or equal to, or less than or equal to. And in those cases, the numbers that come from the top, which are a part of your solution set, will be bracketed, and the numbers that come from the bottom will be parenthesed. Because you can't have the bottom being 0, that's never okay. But if the top is 0, that makes the whole thing 0, and 0 is greater than or equal to 0. If it's a strict inequality, just strictly greater than or strictly less than, no or equal to, then it's always going to be parens. Real quick, let me take a look at the graph of this thing so you can make the connection between the graph and the inequality. I'll call this -9. Call this -3/2. Whoa, shit, I should not have drawn a vertical asymptote at 9. So let me draw this graph again, sorry. The VA is at -3/2. Something else is going on at -9. That's an x-intercept, because that's where the top is 0. My horizontal asymptote is -1/2. So y equals -1/2. I'll draw that like this. If I wanted to graph this function, I would begin by drawing the intercept and asymptotes. My y-intercept is -9 over +3. That's -3. And that is it. So I would end up doing something over here. I know I'm negative. Actually, let me see. Yeah. Going something like, now the scale here is going to look a little bit off. Like this, and then like this. So if I ask, where is this function greater than or equal to 0? You see that it's exactly in here. Everywhere else, the graph is below the x-axis. Yeah, Ronald, I don't know if you heard me at the start of class. I've uploaded that. It's just that YouTube took it down. I re-uploaded it again this morning.
Oh, okay, perfect. Thank you. Because I had missed that first lecture, and like right now I'm like trying to like pay attention. I don't understand anything at all.
I see. Yeah, you will want to rewatch that.
Okay, I will.
Okay, so I'm going to keep going in order here. I want to make good use of your time and mine. I'm going to go through these problems in the order they were requested. We'll make sure that at least one of these involves some synthetic division. Homework 6, I'm on the homework. Homework 6, a question about 1. Frankie, which one did you want to see? Do you mean problem number 1? Problem 26. All right. So I think I'm in homework 7 here. Homework 6. This might hit our long division request as well. So we want to find all the zeros. Yeah. And they ask us to enter with repetition. So I'll write the thing down. This is homework 6, number 26. Okay. Well, there was a request to talk about division, and this gives me an excuse to do that. So I'll go ahead and do this anyhow. X to the 4 plus x cubed plus 14x squared minus 16x minus 32. So we want to find all the zeros, aka roots. So here I'm going to need to do some division. Synthetic division is the fast way. I employ the rational roots theorem. Here are my p's. Divisors of 32 are 32 itself, 16, let's see, 8, 4, 2, and 1. Those are all the divisors of 32. And divisors of 1, my q's are just 1. So the possible rational roots are plus minus all the ratios where the p numerator comes from this list and q, the denominator, comes from that list. So that's plus minus 32, plus minus 16, plus minus 8, plus minus 4, plus minus 2, plus minus 1. You can check 1 easily just by adding up all these guys with x equals 1 plugged in. That would be 1 plus 1 plus 14. That's 16. 16 minus 16 is 0. Minus 32 is certainly not 0. So 1 is out. We can try -1 using synthetic division. So I write down the coefficients. I bring this guy down. I add, multiply these two and then add, that's 0. 0 times -1 is 0, plus 14 is 14. -1 times 14 is -14. If I add these up, I get +2. -1 times +2 is -2. So this is -34. So the remainder here is -34, which is not 0, which tells me that -1 is not a root. Since we already checked +1 just by plugging in, I can rule out both of those and move on to 2. Oh wait, this should be a -16. Sorry, I wrote this down as a +16. It should be a -16. Does that change things? So that would be -1 times -14 is -16 plus -14 is -30. So this should be, sorry, -30 times -1 is +30. But this would still just be -2, which is not 0. Okay, so -16, -32. The fellow we're checking here this time is 2. 1, 1, 14, -16, -32, 1, 1, 14, -6. All right. So we'll pull this down. 2 times 1 is 2. Sum those, we get 3. 2 times 3 is 6. Sum those, and we get 20. 2 times 20 is 40. 40 and -16 is 24, right? +24. 24 times 2 is 48, plus -32 is positive, what is that, 16? Yeah, which is not 0. So we can check -2. I'm optimistic here. And then Frankie, after we wrap this up, I will. It does matter if the number you're checking is negative or positive, yeah. So here you'll see the contrast, right? I'm checking +2 there and -2 here. -2 times +1 is -2. And when I add those up, I'll get -1. When I multiply these, I'll get +2. And when I add those, I'll get 16. When I multiply this, I'll get -32. Oh, damn. Oh, wait, let me see, I'm sorry. Oh, no, this is correct, yeah, 16. Yep, 1, -2. I had high hopes for this, but it looks like it's not gonna work. +2, 14 and 2 is 16, 2 times -2 times 16, -32. When I sum these, instead of getting what I wanted, I will get -48. And then this will be +96. And when I add those, that's certainly not 0. Okay, so I'll have to try something else. The 2's have both been checked. Neither of them worked. Double checking, 6, 20. And that 14 is supposed to be positive, right? Yeah. So that's 40, it's 24. Yeah, okay, so both of the 2's are out. 4 is next. And we run through this until we find one that works. 1 times 4 is 4, 4 plus 1 is 5, 5 times 4 is 20. 20 and 14 is -34. And we're already in trouble here. This is -120 plus 16 is -136. No hope here, right? This is -152. times 4 is definitely not positive 32. So then we'll try negative 4. I really had hopes for one of the 2's to work. 1, 1, 14, 16. Oh, the 16 is positive. Yeah, I did write this down wrong. Ah, fuck me. Okay. Yeah, this should be a plus 16, which is sad because now we need to go back. I do think now that 1 will work. Okay. So we're going to revisit it from here. I'm sorry about that, guys. I think looking at this more carefully, yeah, it's x to the 4 plus x cubed plus 14x squared plus 16x. And originally I wrote this down as a minus. That's okay though. This will make life easier on us because now when we plug in 1, we get 2 plus 14 plus 16 is positive 32. So same sort of thing, possible rational roots. Would be plus minus 32, plus minus 16, plus minus 8, plus minus 4, plus minus 2, and plus minus 1. Checking x equals 1 works. We don't even need any synthetic division there. You just plug 1 in. We'll do the synthetic division because we need to find the quotient, except Lily or Leanne wanted to see long division. So let's do that longwise. This works because P of 1 is 1 to the 4 plus 1 cubed plus 14 times 1 squared plus 16 times 1 minus 32, which is 1 plus 1 plus 14 plus 16 minus 32, which is 0. But then to find the quotient, I have a choice. I could do long division, or I could do synthetic division. Since we just saw a bunch of synthetic division, let's do long division. Discovering that 1 works tells me that x minus 1 is a factor. And Frankie, in answer to your question, yes, I don't recommend using division to check x equals 1. It's a waste of time because you can always check x equals 1 easily. When you plug in 1, you're just adding up the coefficients. But you will still need to divide to get the quotient. So if I take my polynomial, x to the 4 plus x cubed plus 14x squared plus 16x minus 32, and I long divide by x minus 1, the way I do this is just by paying attention to the lead terms. So to turn x into x to the 4, I would multiply by x cubed. So I write an x cubed up here. And then I take this guy and I distribute him here. So x cubed times x minus 1 is x to the 4 minus x cubed. And then I subtract this whole row from the row above. X to the 4 minus x to the 4 is 0. X cubed minus negative x cubed. Right? Yeah. Just making sure. X cubed minus negative x cubed is 2x cubed. Right? 1 minus negative 1, 1 plus 1, or x cubed plus x cubed. That's 2x cubed. And then all these other guys come down because I'm not subtracting anything from them. So plus 14x squared plus 16x minus 32. And now I run back through that same loop. To turn this into this, to turn x into 2x cubed, I would multiply x by 2x squared. And then 2x squared times x minus 1 is 2x cubed minus 2x squared. And now I subtract one row from the other. 2x cubed minus 2x cubed is 0. 14x squared minus negative 2x squared is 16x squared. And the plus 16x minus 32 comes down. To turn x into 16x squared, I would multiply by 16x. And when I distribute 16x over x minus 1, I get 16x squared minus 16x. And now it is time to subtract the rows. (16x minus negative 16x is positive 32x. And then I'll have the minus 32 come down. To turn x into 32x, I multiply by 32. 32 times x minus 1 is 32x minus 32. And this time when I subtract the rows, everything goes. So my remainder is 0, which is what we expected, because we knew already that x minus 1 was a factor. The point of doing this was to get the quotient polynomial out and to practice long division. So the result of this whole thing is that my polynomial p of x is equal to x minus 1 times x cubed plus 2x squared plus 16x plus 32. And now I begin again trying to factor this. Since his lead coefficient and his, lead coefficient and constant term are still 1 and 32, my list of p's and q's would be the same. I can try checking 1 here again by plugging in x equals 1, because maybe this is a repeated factor. 1 plus 2 is 3, plus 16 is 19, plus 32 is definitely not 0. We could try negative 1 using synthetic division. So in other words, we start back over on this guy. My list of p's and q's are the same here because the constant term and lead coefficient are the same here. Negative 1, and then 1, 2, 16, 32. We can try these. This is negative 1. Negative 1 plus 2 is positive 1. Negative 1 times positive 1 is negative 1 plus 16 is 15. Negative 1 times 15 is negative 15 plus 32 is definitely not 0. What is that? That's 17, right? Okay, so plus and minus 1 are out. We can try, let's see. Since all of these are positive, we could infer that any root would have to be negative. So let me try negative 2 next. Negative 2 times 1 is negative 2. These sum to 0. Negative 2 times 0 is 0. These sum to 16. Negative 2 times 16 is negative 32. Joy of joys. So negative 2 is a root. And this tells me that my polynomial, I've got my x minus 1, that's still here. And then this piece can be rewritten as x plus 2 times x squared plus 16. X squared, I'll write the 0x plus 16. So in other words, p of x, if your goal was just to factor it into linear and irreducible quadratics, looks like this. But remember, we wanted all the roots. I don't remember if we wanted real roots or all the roots. So the real roots here are x equals 1 and x equals -2. All roots, real and complex, would be 1 and -2. And then also the roots of this. If you set x squared plus 16 equal to 0, you get x equals plus and minus the square root of -16, which is 4i and minus 4i. So this is your complete list of roots. This is as far as you could hope to factor this thing using real numbers only. And if you wanted to factor this all the way down, it's x minus 1, x plus 2, x minus 4i, x plus 4i, like that. Okay, so killing several birds with one stone there. We got to practice some long division, some synthetic division, and some nifty factoring tricks. I am going to keep going in the order the questions were asked in order to be fair to the folks who asked them quickly. I do think, yeah, that means Fabrice's questions are next. 3, 4, 5, 6, and 8 on the quiz, though. That's a lot of questions to do in one sitting. Fabrice, which one would you most like to see? Maybe pick 1 or 2 of those 5 that you asked to see. Oh, that's right. And Frankie wants to see 29. So Fabrice, I'll ask you to pick 2 of those. I'll do 1, then I'll do Frankie's number 29, and then I'll come back and do your next one. And then we need to keep circulating to be fair. So 3, 4, 5, 6, and 8 on the quiz. Fabrice, which one would you most like to see? Four and 6. Okay. So number 4 we're looking at here. They ask, what's the smallest possible degree? And for an explanation. So rather than solving exactly this problem, let me look at a couple sort of examples here. And try to make some statements about the smallest possible degree. Whoa, shit. All right, sorry. Didn't mean to get all funky on you there. We've seen lots of graphs that look like this. What's the smallest possible degree of a polynomial whose graph is parabolic like this? Could that ever be a linear function? Something that just has largest power of x being 1? Give a graph like this? Can help me with this. What does this look like to you? It's like a parabola, right? Quadratic. The smallest possible degree here is 2 for several reasons. You've got 2 x-intercepts, which means you gotta have at least 2 factors. If you got 2 factors, you gotta be at least quadratic. So smallest possible degree is 2. All right. Notice that the minimal degree is 2, and you've got 1 local max, 1 turning point. Yeah, so the relationship here is that the minimal degree is 1 more than the number of turning points, or the number of turning points for a degree n polynomial is at most n minus 1. What's the smallest possible degree here? I've only got 1 x-intercept, but this couldn't possibly be a linear function. Look how curvy it is. It's not quadratic because this is not a parabola. From the end behavior going down on one side and up on the other, you know the degree has to be odd. This fellow has 2 turning points. And he only has 1 root. But if you shifted it down, it could have 3 roots. And shifting, adding or subtracting a constant wouldn't change the degree, would it? So this has 2 turning points. This is a degree 3, or the smallest possible degree. Is 3, even though he only has 1 root. What this means is that you've got 1 linear factor and 1 irreducible quadratic factor. Okay, how many turning points does this bottom guy have? I got 1, 2, 3 turning points. How many roots does he have? I've got 1, 2, 3, 4 roots. So remember, each root is coming from a factor. So this has to have 4 factors. 4 factors and 3 turning points. What's the smallest possible degree? What's more, it's not possible for this to be a degree 5 polynomial because of the end behavior. The end behavior goes down on both sides, which means it's got to have an even degree. Right? If the end behavior is opposite on either side, that's an odd degree. The end behavior is the same on either side, that's an even degree. So the smallest possible degree here is 4. For questions like this, there's 3 things to think about: the end behavior, the number of roots, and the number of turning points. All right. Every root contributes a factor. So if you have 5 roots, you got to be at least degree 5. Could be higher. Every turning point adds 1 to the possible degree, remembering that you begin with 0 turning points. A linear function has 0 turning points. You've got 1 turning point, you've got to be at least degree 2. 2 turning points, got to be at least degree 3. 3 turning points, got to be at least degree 4. Okay. So while this isn't exactly that quiz question, I don't like answering the quiz questions exactly. This is precisely what you need to answer it. So I want to go back to Frankie's question, which was homework 6, number 29. And then we'll return to Fabrice's question if there's time. Second question there. Now, if 29 is identical to the one that we did, I don't want to burn too much time on it. No, this is a little bit different, but it's very, very similar. So here we would begin again with our rational roots theorem. X cubed minus 2x minus 4 So my possible rational roots are all the divisors of 4 over all the divisors of 1. That's plus minus 4, plus minus 2, plus minus 1. We can check 1 itself just by adding up the coefficients. 1 minus 2 minus 4 is negative 5. So we can rule that out right away. Can check negative 1 using synthetic division. This guy, remember, is x cubed plus 0x squared minus 2x plus 4, minus 4, sorry. So the coefficients, when I write them down for synthetic division, would be 1, 0, negative 2, negative 4. Bring down the 1. Negative 1 times negative 1 is positive 1, plus negative 2 is negative 1. This is 1, this is negative 3, which is not 0. So we move on to the 2's. This is 2, 2, 4, 2, 4, and 0. So that works. Focus, you fuck. Sorry, yeah, this camera's got a mind of its own sometimes. So we check 2 with synthetic division, and he works great, which means that my polynomial p of x can be written as x minus 2 times the quadratic whose coefficients are here. That's x squared plus 2x plus 2. X squared plus 2x plus 2 is an irreducible quadratic. You can try factoring him and you'll have no luck. So we use the quadratic formula. B squared here is 4 minus 4 times 1 times 2 is 8. All over 2a, which is 2. So this is negative 2 plus or minus the square root of negative 4 all over 2, which is negative 2 plus or minus 2i over 2, that's negative 2 over 2 plus and minus 2i over 2, or negative 1 plus or minus I. So these are the complex roots of this polynomial, the quadratic part here. So here's that thing factored into linear and irreducible quadratic pieces. And if you want to factor all the way over complex numbers, you would have x minus 2 times x minus negative 1 plus I times x minus negative 1 minus I. That is our fully factored over the complex numbers polynomial. All right. So Fabrice wanted 4 and 6, and I don't think I've seen anything else requested that we haven't addressed. So let me pop this quiz back open and see what number 6 was asking. Yeah, this is fine. So find a polynomial of the specified degree whose graph is shown. Degree 3, graph looking like that. Oh, degree 3 graph looking like this. All right, so what are my factors? Let me modify this a little bit. Again, I don't want to spoil the quiz problems. let's call this -1, call this 1, I'll call this 2. Yeah, how about that? All right. So if this is my, I would expect, I did switch it, yeah. So the vertical, the y-intercept doesn't give you any factors. Remember, factors come from x-intercepts. So if I told you that this down here was a y-intercept of -4, that doesn't mean I would have a root or a factor associated with -4. So we want to find the equation. Well, my roots are x equals 2 and x equals -1. Those are my x-intercepts, so those are roots, which means that factors include x minus 2 and x plus 1. But there's something else that you need to infer here. What's the multiplicity of the root at -1, or what is the least possible multiplicity? Yeah, we bounce off the x-axis there. So we know that the multiplicity of the root here is even, which means that this has to be like x plus 1 squared. So this guy could be multiplicity 1. This guy has to be at least multiplicity 2. Couldn't be multiplicity 3 because then that would also be a cross, but it could be multiplicity 4 or something like that. But they told us that the degree is 3. So my polynomial p of x definitely has as its factors x minus 2 times x plus 1 quantity squared. That is a degree 3 polynomial. But it doesn't have the right y-intercept. So we have to allow for the possibility of a lead coefficient being different from 1. I know from the graph that p of 0 is -4. But p of 0 here is a times 0 minus 2 times 0 plus 1 squared. So that has to be equal to -4. This is the same as -2a equals -4, so a has to be 2. So the polynomial of degree 3 having this graph has to be 2 times x minus 2 times x plus 1 quantity squared. All right. So you guys have done really good working through all of this polynomial business and the rational function business. I'm proud of you. You've put in a lot of work. Make sure that you continue to put in a lot of work over the weekend, right? Or, weekend, but it's Wednesday. Between now and Monday, put in some time. Make sure you're very comfortable with all the quiz problems, right? Like very comfortable. You want to make sure that you thoroughly understand all the concepts behind the quiz problems. Unfortunately, I am out of time for this class here today. I've got an office hour and I've also got a boatload of grading I need to do. Right, so if you want to go back to the previous problem real quick. Matthew, which problem did you want to go back to? This one? If you want to talk about more problems, you can come by my office hour. I do have an office hour today from 3:30 to 4:30. Oh wait, and this class, I've got you guys till 3:15. No, we have time for a few more. Yeah, okay, let's go ahead and do 29 then. Yeah. No, you're right. I was thinking 3 o'clock, but it's 3:15. 315 is the end. I believe this was that problem, right, Matthew? Factoring x cubed minus 2x minus 4 all the way down into irreducible quadratics and linear factors, and then factoring all the way down into linear factors over the complex numbers. All right, I got another one for you guys. And this is related to one of the extras that Fabrice that you asked for. Can you find a polynomial with integer coefficients having roots let's say 3, -1/2, and 1 minus I? Vincent, I'll ask you to clarify that question just a little bit after we finish this one. I think there should be time for both. So if I want integer coefficients, integers are real numbers. I know. So this is just scratched out. So 3, -1/2, and 1 minus I. Each one of those tells me a factor. There's a little something else that we want before we say that. So definitely this tells me that x minus 3 is a factor. This tells me that x plus 1/2 is a factor. And this tells me that x minus 1 minus I is a factor. But there's one other factor that I need in order to guarantee the coefficients being real. Almost. Yeah, 1 plus I. The complex conjugate of 1 minus I. So that means that x minus 1 plus I is a factor. So then my polynomial would look like, my polynomial could have any lead coefficient, a, but must have the factors x minus 3, x plus 1/2, x minus 1 minus I, and x minus 1 plus I, exactly like this. If I multiplied all of this out, would I have integer coefficients? I'll take care of this middle guy here for you. This would be x squared minus 2x and then minus minus makes plus. This times this is 1 plus. I'll do it off the side. 1 minus I times 1 plus I. That's 1 minus -1 plus 2. Oh yeah, we've seen this guy before today. All right. So if I multiply all this out, would this have integer coefficients? Say without the a here? Or would I end up with some fractions due to this 1/2? So I chose this problem for two reasons. I wanted to drive home that the easiest way to do this is to use a equals 2. Because then I can push that into this x plus 1/2 factor, and I get x minus 3, 2x plus 1, x squared minus 2x plus 2. And now without multiplying it out, you can tell that this will have integer coefficients because it already has integer coefficients. And when you multiply those out, you're not going to introduce any fractions, you're just multiplying whole number pieces. So in other words, another way to start here would have been to use 2x plus 1 as my factor for the root negative 1/2. So make sure you remember that complex roots come in complex conjugate pairs. When you form the factors out of those complex roots, make sure you put the complex root here in parentheses, like I did here, right? X minus paren 1 minus I, x minus paren 1 plus I. And then if you want an integer coefficient polynomial to have a fraction root, you can always do it like this rather than like this. All right, there was one other thing there, right? What did you guys want to see? Benson, what do you mean by negative quotient? Could you give me an example or?
Professor, can you go back to a long division of polynomials? I have a question about when it's negative, one of the numbers. Instead of all positive, when it's negative.
Sure, we can look at another example of long division where one of the terms in the quotient is negative. Frankie, to answer your question, these two pieces I multiplied together in my head to get this piece. And then I chose to plug in 2 for a because I wanted to get rid of this 1/2 here. Because we wanted integer coefficients, integer meaning whole number, no fractions. Okay. We want to do a long division problem where a term in the quotient is negative. Sure. Yeah. Let's try long dividing. 2x cubed minus 3x squared plus 4x minus 1 by x plus 2. So I pay attention only to the lead terms. To turn x into 2x cubed, I would multiply x by 2x squared. 2x squared times x plus 2 is 2x cubed plus 4x squared. And then when I subtract these, I'll get 0 here, and then minus 7x squared plus 4x minus 1. To turn x into negative 7x squared, I would multiply by negative 7x. So here's a negative term in the quotient. Negative 7x times x, as designed, is negative 7x squared. Negative 7x times 2 is negative 14x, and again, I would subtract. These two come to 0. 4 minus 14 is negative 18 x, and then minus 1 is minus 1. And then finally here, x, to turn that into negative 18x, I would multiply by negative 18. So I'll get negative 18x minus 36, minus 34, sorry. Oh no, 36. Yeah, sorry, 36. Right, the first time. These two subtract to 0, negative 1 minus negative 36 is negative 1 plus 36 is negative 35. So here I would learn that 2x cubed minus 3x squared plus 4x minus 1 all over x plus 2 is equal to 2x squared minus 7x minus 18 plus negative 35 over x plus 2. So here is your quotient, and he does have some negatives in him. Your remainder also happens to be negative here. Does that satisfy the question, Benson?
Yes, thank you.
Cool. Alrighty then, I do think I gotta get going now. Yeah, we're a couple minutes over, it's okay. If you want to talk more about problems, I do have an office hour this afternoon. Otherwise, I will see you guys after the test. So remember, Monday is your exam, same rules as for exam 1, same setup and everything, just different material. If you anticipate having any problems getting a webcam with your internet connection, anything like that, scanning problems, please try to remedy those before the day of the test. So if you reach out to me, I can help you as much as possible. The college does have loaner laptops if you need to borrow one of those. With working webcams, you can make arrangements to take the test in the testing center, although I've been asked to not send people to the library. So if you need to use the college's Wi-Fi or other things, the testing center there is the way to go. We can schedule that. Yeah, HonorLock's ID scan thing can be kind of annoying. It might help if you like set your ID on something, like set it in your keyboard tray or something like that, and then hold your keyboard up to the camera. That way you can hold it extra still and extra stable. But you know, we can experiment with that. Yeah, if you have a laptop, we'll need to get creative, but something to hold extra stable and give the camera time to focus will help. I can enable a practice quiz on HonorLock, so you can experiment with the ID verification process. I'll go ahead and do that right now. But then if you have other questions, comments, concerns, please reach out to me, and please do so as soon as you can. Don't wait until the test and run into problems while you're trying to get into the test, because then you'll lose test time. Okay, that's it. I will see you guys after the exam. Study hard. If you have questions, please ask.